Hello and welcome to section 3.8 on implicit differentiation. Implicit differentiation allows us to calculate the derivative of functions written implicitly rather than explicitly. As many students are unfamiliar with implicit functions, they will be the focus of this pre-lecture video. Take for example the equation y equals the square root of 9 minus x squared. This equation graphs the top semicircle on a circle. How do we know this? Well, squaring both sides and moving x squared to the left-hand side, we obtain the equation of a circle. Remember, the equation of a circle fails to be a function as a circle fails the vertical line test. The equation of a circle, though not a function, defines two functions, the top semicircle and the bottom semicircle. In fact, there are multiple functions implied by the circle equation, not just the top and bottom semicircles. We can take the piecewise function f, which gives the top half of the circle when x is positive, and the bottom half of the circle when x is negative. Or we can define a function g by taking the domain of our circle and chopping it into pieces, and just choosing a y segment for each piece, either the top or the bottom. We now have our function g graphed in red. It is a function as it passes the vertical line test. When a function is written in the form y equals f of x, where the y variable only appears on the left-hand side, we say that the function is explicitly defined. The equations of the top and bottom semicircle are written explicitly. In fact, almost every function that we've worked with in this class up to this point has been written explicitly. When a function is hidden inside an equation, that is, a function of y depending upon x that is implied by the equation, we say that the function is implicitly described. Take the equation of the circle. We have seen four functions which are implied by this equation, and there are many more. Explicit, as in for a given x, the value of y is clearly understood. Implicit, as in for a given x, the value of y is implied by the equation. You still need to solve an equation to find out what y can be. For example, if in our circle equation we are told that x is equal to 2, the y value is then implied by the equation 2 squared plus y squared equals 9, or y squared equals 5. So when x is equal to 2, y must satisfy the equation y squared equals 5. As we know, there are two values which satisfy that equation, the positive and negative square root of 5. It is not clear from the equation which one is needed for the function we're interested in, but there are only two values which it can take at x equals 2. Not all functions which are presented implicitly can be written explicitly. How would you solve these equations for y? For our purposes, it will not be necessary to write implicit functions explicitly. In our second video, we will extend our differentiation techniques to implicit functions. As a final example, let's take a look at the graph of the top equation. Our equation defines a curve, and it implies many functions. All we need to do is erase enough of the curve so that the remainder of the graph passes the vertical line test. Notice that the only vertical line test issue happens in the loop. And if we erase enough of the loop, we have the graph of a function. General curves still have tangent lines, which along with implicit differentiation are the topic for our next video.